When we talk of the mathematics of quantum mechanics, we get confused with terminologies and notations like Hilbert space, complex conjugate, eigenstates, Hermitian operator, and there are many. However, the mathematics of quantum mechanics and the fundamental concepts stem from some of the fundamental rules of quantum mechanics. So once we understand them, quantum mechanics becomes a cakewalk. After all, it is all about observation and measurement. In this video, you will be learning the mathematics and the foundation principles which designs the framework of quantum mechanics. My name is Shaunak and you are watching this video on my channel Physics for Students. Welcome to the mathematics of quantum physics. Well, first what I would like to tell you is that there are certain mathematical postulates, and these postulates basically forms the framework of quantum mechanics. So we would first understand the mathematical postulates but in a very easy non-mathematical manner, and then we will start exploring what is the mathematics of quantum mechanics or quantum physics which are involved in it. So first of all, the quantum mechanics as we know is not about mathematics, but I say that quantum mechanics describes the behavior of atoms, molecules, photons, and we use mathematics to quantify, model, and in order to understand them. So there are 5 simple postulates that fully encapsulates the mathematical model of quantum mechanics. That means these 5 postulates, if we understand them closely, we will understand the mathematics of quantum mechanics clearly. So the first question is that what are those mathematical postulates and how we can understand them, coming up in the next part of the video. So first let us see what is the first postulate that talks about in a very technical term. Well, the postulate tells that the state or wave function of individual quantum systems is described by unit vectors living in separate complex Hilbert space. First of all, let us break down this postulate into simple English terms and let us understand the meaning. So first of all, what we get from this is a term called quantum systems. I would request you that you imagine really tiny things like atoms or particles, and these are actually what we call quantum states. The second thing what comes is that state of a system or a wave function. Think of the state as the complete description of one of those tiny things. It is like saying what it is doing, where it is, and everything related to that. Unit vectors. Now unit vector is like an arrow pointing in a specific direction, but it is always have the same length. So it is a way you can say to describe a specific condition. Then comes complex Hilbert spaces. Well, don't worry much about complex Hilbert spaces. Just imagine it is like a big playground where these unit vectors live. Each tiny, I would say, thing in quantum system has its own playground. So putting all of these things together, what we get is that this one. The state or the conditions or a complete description of tiny things which we call quantum systems is like an arrow pointing in a specific direction in its own playground, which is called the complex Hilbert space. Each tiny thing has its own arrow that tells everything about that particular state. Now this helps scientists actually to understand and talk about those tiny things, and they behave according to the quantum world. This is overall what I can say you a very basic understanding of postulate 1, first postulate, but we are going to describe mathematically. But first let us see what is the second postulate. So read it aloud. The probability of measuring a system in a given state is given by the modulus squared of the inner product of the output state and the current state of the system. This is known as Born's rule. Immediately after the measurement, the wave function collapses into that state. So let us break down slowly into small parts. Probability of measurement. So you can imagine you're playing with a tiny toy, with a device and a doll, and you want to know where it is. So the probability is like asking what is the chance of finding the toy in a certain spot, here or there. Well, inner product, I can say you think of the inner product as a special way of comparing two things. In our case, you can take it is like comparing the current state of your doll or your toy before you check and the state that it will be after you check. This is something technical, modular squared. You can say something, it is just a fancy way of saying that the inner product, to take the inner product, make it positive by squaring it and ignore whether it is positive or negative. So this is something which is called modular square. Born's rule, well, this is by Max Born, a famous physicist. Born's rule, you can think, is the formula that helps us to find the chance of finding our toy in a certain state. So it involves doing this special comparison, which I told to be the inner product, squaring it, and that gives us the probability. The wave function, I think most of you know the wave function collapse. So when you actually check where your doll or your toy is, the wave function is like the description where the toy could be. After you find it out, the description collapses to the exact point or the place where you found it. So overall, postulate 2 can be framed up in a simple language like this. In simple terms, we can say Born's rule is like a magical formula that helps us to predict the chance of finding something in a certain way, and when we actually look to find it out, the description of where it could, I would say the description of where it could be become very specific, and that is what we call a wave function collapse. The third postulate is something like this. The quantum operators are represented by unitary operators on the Hilbert space, a consequence of the Schrödinger equation. Okay, let us break it down into simple terms. Quantum operators. You can imagine it, you have a special way of changing or doing something to these tiny quantum things, like a particle of an atom. So this special way is what we call quantum operation. The unitary operators, think of it as a unitary operator as a magical tool that you use to change or transform something. It is like having a special magic wand that makes things happen. Hilbert space, we have actually discussed earlier. It is like the playground. We talked it where the tiny things like the quantum systems live, and the Hilbert space is a way to describe all those possible states these tiny things have to be in. Schrödinger equation, well, this is a kind of a fancy equation that describes how things change in the quantum world. It is, a kind of a set of rules that tells how our quantum system evolves as the time passes. So can we put it together? So here it is. What we want to do is something special to those tiny things in the quantum world, like change of its state. We use a magical tool called a unitary operator. This tool follows certain rules described by the Schrödinger equation, and it works in the playground of all possible states, and this playground is known as the Hilbert space. So in simple terms, we can say that it is like having a special magic wand, the unitary operator, and to make change to our things in their special playground Hilbert space, and we follow some rules, that is the Schrödinger equation, and it works and it does things properly. So when we want to do something special to those tiny things in the quantum world, you use the magical tool quantum unitary operator as described by the Schrödinger equation, which happens in a space which is called the Hilbert space. Okay, what is the postulate 4 of quantum physics? Let us find it out. It says that the Hilbert space of a composite system is given by the tensor product, also known as the Kronecker product, of the separate individual Hilbert spaces, right? So again, let us break it up. Hilbert space I'm not going to define, it is already known. Well, composite system is something that you can imagine you have two or more of these tiny things, I mean to say quantum system, and you want to talk about them together. So that is what togetherness is called, composite system, just a group of these tiny things. Okay, tensor product, I would say you can picture this as combining the two sets of toys or dolls, whatever, and if you have one set of toys in one box and another set in another box, the tensor product is like putting, I would say, them side by side to make a bigger set, right? And each toy from the first set can pair up with every toy of the second set. So in simple terms, what we can say is that when you have two or more groups of tiny things, I mean to say composite system, the Hilbert space of all of them together is like the combining their individual playgrounds. It is as if you are putting the little different things of toys side by side, and each toy from the first set can play with every toy of the second set. So this is, I mean to say, in a very lucid term, what is called postulate number 4. What is the fifth postulate? It tells that physical observables are represented by the eigenvalues of a Hermitian operator on the Hilbert space. Okay, so what is physical observables? These are things that we can measure. I'm going to say these are things that we can measure about a system. For example, position, momentum, or energy of a tiny particle are physically observables. Eigenvalue, right now let us think of these as special numbers associated with a certain property of the system. Each observable has its own set of these special numbers. Hermitian operator, you can think is as a tool that helps us to figure out these special numbers. It is a mathematical way of representing the physical observables. Hilbert space, nothing more to tell about. Taken together, we can say that when we want to measure something about a tiny thing in the quantum world, like its position, energy, or whatever, we use a special kind of a tool, Hermitian operator. This tool gives us a special number, which are called eigenvalues, that helps us to understand the property of the system. It is just like it is using a mathematical trick to figure out the important details of a tiny things that plays in the playground, which is the Hilbert space. Now, I have already made a very detailed video. You can go back to my channel Physics for Students and look into what is called the Hermitian and Hamiltonian operator, what is the relation and what it is all about. In my channel Physics for Students, you will find a very detailed video on Hermitian and Hermitian operator and Hamiltonian operator. Okay, now that we have understood all the 5 postulates on a very crude, on a very simple language, now it is the time that we should go back to postulate 1 and we should try to discover a little bit more. So if you refer to postulate 1, you see the finite dimension vectors are a great way to represent, I would say, the state of the quantum system, something which is very finite. We are not going into the Hilbert space, which actually takes the infinite part. When the physical variables only have discrete possibilities, that means it can go on the left, on the right, and the up and the down. So this treatment of quantum mechanics is, the physical variables having discrete possibilities is done by what is called matrix mechanics. And it is very well suited, in kind of a quantum information and quantum cryptography, etc. But what about when we want to describe physical things that have continuous values? These are discrete, but what about these continuous values? Such as, for example, the position of a straight line or something. In this case, we need a vector of, space of infinite and continuous dimension. And it turns out to be possible to define it in a Hilbert space, and this is referred to as something which is called wave mechanics. So we went from finite to infinite, and for infinite we need something which is infinite and continuous, and it is possible to define in a Hilbert space. Although in details of Hilbert space I will be covering in the next part of the video, but this is a kind of an understanding. So this is one postulate 1. We will go more into the mathematics of postulates. Now, the question that arises is, all those 5 postulates are great. 1, 2, 3, 4, it gives up different mathematical properties of quantum physics. But the question is that this one, why do we at all need postulates in order to understand the mathematics of quantum mechanics? Let us look into a possible reason that why do we need postulates. Now, you see that scientists have derived a series of axioms that result in a set called postulates of quantum physics. And these actually are assumptions, because without assumptions, how can we go up in our scientific endeavor? So at the root level lies the postulates, and the pyramid is the scientific theory. So as we go up and up and up and up, you see the cone actually shrinks to a certain point. And that is all about intuitive understanding, philosophical understanding, or whatever, right at the apex. So these are the fundamental assumptions. It gives the outline of the basic concept of rules and behaviors. And from here we go into the scientific theory, which allows us to describe and understand the behavior of particles at the quantum level. So we can develop a consistent, a very predictive, and a nice robust theory for the microscopic world. And for that we need those postulates. So you see, in this kind of I would say, quantum system, things are pretty counterintuitive. I mean to say, when we discover. So because it goes beyond our intuition, unreasonable, illogical. Whereas in kind of a classical physics versus quantum physics, classical physics is fully macroscopic, and they cannot fully explain the behavior of subatomic particles. So the question rises is that instead of that, we have a question that what is the purpose of this postulate? Let us look what is the purpose of having a postulate in any kind of a scientific theory. The first thing is that definitely we need it because they define the basic concepts and quantities of the theory. In this case, you can think of wave functions, observables, etc. Second most important thing is that they provide rules, because until and unless you define a postulate, how can you define the rules? And here in quantum physics, we will see a different kind of a rule. The third one is that they establish the principles of superposition, wave particle duality, quantum entanglement, I mean to say the rules and then the principles. And finally, what we also see is that they guide the mathematical formalism, because you will see there are a lot of weird formalism which happens in quantum physics, and that is the reason we need. So all in all, what we can say is that they represent a mathematical framework rather than a complete physical picture of the quantum world. So that is why we need postulates. Now, in order to revisit the first postulate, which actually we went through that, we need to first coin and make an understand of a kind of a notation which is called the bra and the ket, which is very simple, called the Braket notation. So these are actually introduce a new notation which is quite used in physics, and when physicists play with vectors, I mean to say general vectors, to describe a quantum system, they like to change things around. So everything we have defined previously were vector addition, matrix multiplication, inner products, but I mean to say they remains exactly the same. The only thing that changes is basically the way that we write it. Okay, so first let us see what is a ket. So when writing a vector, say for example V, to represent a quantum state, remember quantum state means a state which describes everything, position, momentum, whatever in terms of classical physics you can imagine. So to represent a quantum state, we will use a different kind of a notation as ket, and this is written as a vertical bar and then a V, I mean to say whatever you write, the variable followed by an angular bracket. So what happens is that this is a notation which is commonly used in quantum mechanics, and you see it does not change the I would say the nature of the vectors. That means both notations in this equation right at the left hand side bottom are the same. So whether you write it in ket form or you write it in a vector form, it is the same. So now the question is that the point is that this is a notation which is used in quantum mechanics. Remember, nothing changes according to the nature of the vector as well. Now what is a bra? So the conjugate transpose of a ket, if I take it, is defined by this, either by a dagger sign or I can put up a horizontal bar, either way. So we can see this one, I would say the conjugate becomes the angular sign. So the conjugate transpose of a ket is denoted as the bra. So for a bra we get a angular sign, then the variable followed by the left sign, right? And the earlier was the ket, which has got a horizontal bar and then the variable and what. And again the fact that is just a notation, it does not change anything. And what is called a bracket? So given two vectors V and W, say for example, both in the ket form, we use the following notation to denote the inner product, which is this one, and this particular one is known as the bracket of the vector V and the vector W. So we join that, we take the inner product, and this is what is known as the bracket. Now there's something very interesting, a kind of a very important thing that comes up. You see that in terms of geometry also, if we take this and this, and then we take this and we take this, we get this. So I mean to say, if you recall the properties of the inner product of the vectors V and W, then we can already get this. Okay, so one thing which is very, very important, which I would like to show you that comes out of that, is that if I take this kind of a vector doing an inner product, from here it follows this one. So what does it say? It says that the inner product of two vectors is equal. So v and w get shifted to w and v to the complex conjugate of the inner product, and the vectors are in reverse order. Obviously v and w on the left hand side would be w and v. Okay, now let me demonstrate this particular, I mean to say that inner product of the two vectors and the complex conjugate with a very simple example, and I'm sure that you're going to enjoy it. So let us assume that we got two vectors, v equal to this one and w is equals to this one, and if we calculate the inner product, we get to this and we get this one. So the left hand side is the result of the inner product, 1 minus I divided by 2. And in the same way we can calculate the inner product of this, and I would say strangely enough we get this. So what we prove is that the inner, just what we told, that the inner product is basically the complex conjugate. So automatically 1 minus I becomes 1 plus I divided by 2. So that is, we have proved that. So this is basically, we are going to use extensively in the further mathematics of quantum mechanics, which is called the Bra and the Ket notation. Together it is called the Braket notation. Now we need to understand, if you go again and revisit the first postulate, there is some word and something which is called a quantum state. Now in the next part of the video, I'm going to explain you with a very simple and a very beautiful example that what is actually called is a quantum state. Okay, so postulate 1, as you can see, it states the state, and we are going to understand what is a quantum state. Now see, in quantum physics, a quantum state is basically a mathematical entity that embodies the knowledge of a quantum system. I'm to say, in quantum mechanics, specifies the construction, evolution and measurement of a quantum state, and the result is basically a quantum mechanical prediction for the system which is known as the state. Now hold on, I will try to break this line what I just told into simple terms. So the what you need to first understand is that the result is a quantum mechanical prediction for the system represented by what is called a state. Now the knowledge of the quantum state and the quantum mechanical system, I want to say quantum mechanical rules for the system's evolution in time, gives us all that we know about a quantum system. That means we have got a state and we know the quantum mechanical rules for the system's evolution in time. It will give you everything that you need to know about the quantum system. So what we can say from here is that it is definitely a mathematical entity. It specifies the construction, evolution and measurement of a quantum system, and the knowledge of the quantum state and the quantum mechanical rules for the system evolution exhausts all that can be known about a quantum system. Now strangely enough, what we are doing quantum mechanics, but this concept of a state actually emerges from none other than our good old classical physics. Let me take you through an analogy of comparing classical physics quantum state and what is called the quantum physics quantum state, so that things will become much more clearer. So here it is, a typical coin. I mean to say, once it is flipped and it falls on the ground or your hand, it is either a head or a tail. This is very classical in nature, and the values are all R, that means real number. So a classical dynamical state consists of a set of dynamical variables with well-defined real values at each instant of time. So you take up each instant of time, a coin flipped up or a cannonball throwing a ball jumping around a frictionless ground, all of this actually gives you the state, and this gives a real number value. Considering to that, when we get to a quantum state, it's just an example of superposition. It actually is the values that derive from the quantum states are complex numbers. First of all, not real numbers. They are quantized, and these are, go up to infinity, and they're limited by uncertainty relations and only provides a probability distribution of the outcomes for a system, doesn't give you the real certainty. Now the question is that how do we represent a physical state using vectors? That means we talk about a state. How do we represent that? First we have to find out that. And before going into that, I would request to those who are watching this video to look into this video, because this is a very detailed video which is called The Nature of Classical Physics. And here I have actually talked in details about what is a classical state, what are a 1-state, 2-state, 6-state system, infinite state system, a stroboscopic effect, lot of those things, because until and unless you understand the nature or the state of a classical physics system, you won't be able to understand that of a quantum system. So you can have a look onto that. It is there on my channel, Physics for Students. And if you're watching this video and you're finding it really interesting, please do subscribe to my channel. Click on the bell icon to get all the notification from Physics for Students. So we come to the questions that how do we represent a physical state using vectors? For that, what I need to do is that we have to introduce a concept which is called exclusive states. Okay, what do I mean by that? Then, for example, when we are modeling the state of a given, I would say a physical quantity, whatever be it, two states are said to be exclusive if the fact of being in one of the states with certainty implies that there are no chances whatsoever of being in any other states. For example, we take box A, B and C, and if I know this particle or electron is here, then we know that it is not here and not here. So that is what is called an exclusive state. Now if I take I would say a kind of a say for example a kind of a value which tells that the this particle is moving in this part, in this oblique direction as well as in this, then we can say these three states are definitely not exclusive. Why? Because moving in this blue direction is also the same as moving in the x direction as well as the y direction. That means horizontal and vertical. That means I mean to say this the blue one which is diagonal. So moving diagonally, I mean to say I can say that I'm moving in the x direction as well as the y direction. Right. So moving diagonally. So that means it is what is not an exclusive state. Now I would like to make you recall from one of the very basic properties of vectors is that orthogonal vectors, we said when we say that orthogonal vectors are orthogonal, we say that two vectors are orthogonal when they are perpendicular if their inner product is 0. So let me cite you a quick example. If I take this and this and I take an inner product of this, it gives you the value this equals to 0. That means these two vectors are orthogonal. Okay. Now let me take you through this example. On the left hand side corner you can see the particle movement, I mean to say what I cited, and here you can see this figure. Now what I am trying to make out of this figure is that you see the projection of this one, the P, V and W. That means which one? This one, underlined on the left with this circle. If you want to see once more, this one. So the what happens is that the projection of this I mean to say V onto W, which is V, this and this. So the projection of P sub VW of V onto W is given by the component of V along the direction of W. So I repeat, the projection of P sub V comma W of V onto W is given by the component of V along the direction of W. Now since we define it as the component of W, so this part is basically what is called a scalar. This is just a recap. I mean to say this is projection and orthogonality. I'm trying to give you an understanding. Now from here what we get is that from this orthogonality and the concept of projection, we can actually define a new concept. I mean to say we can get out a relation. But before that, look into this figure. These are orthogonal vectors, and what we say is that the arrows are pointing at angles which are like the corners of a square, and they have a dot product of 0, meaning they are completely independent to each other. This is on the right hand side what is called the image of projection. And a projection is basically of A onto B is this A1, the green one. And you can think of projection as imagine shining a light straight down on a flat surface or anything, and the shadow of an objection is a projection onto that surface. So when we are projecting a vector onto another vector, that means you can say that we are trying to find a shadow, finding its shadow or the reflection along the direction of the vector. From here, what we come to know is that when two vectors are orthogonal, it signifies they are perpendicular because the dot product is 0 and so on. That means this has direct implication on their components. And a vector cannot have any component along a vector that is orthogonal to it. And the reason is quite obvious, because components represent how much vectors point in this direction, x, y, or whatever direction. And if the directions are perpendicular, that means a vector cannot point along its orthogonal vector. So from here we come to the point that components of a vector along its perpendicular direction is always 0, obviously. Meaning that when a vector is projected onto a line that is perpendicular to the component of the vector in that direction will always be 0. If we take this one, you can, you can just read through this and you can even go back and understand this concept, because I'm taking this concept forward that given vector has no components along of its orthogonal vectors, we can make a connection between exclusive states, which we just saw, and the orthogonal states. Or exclusive means that we know that the particle would be here or whatever be it. And we also know what is non-exclusive. So from here what we can tell that given a kind of a quantum state with n exclusive states, whatever be the number, each state will be represented by a vector, obviously from an orthonormal basis of n-dimensional Hilbert space. Now this is a kind of what I would say what we talked about that, because the n exclusive states and not exclusive states, I have already told what is the exclusive state and what is not. Now if I get from here to here, we know that so the state of the electron can be either at box 1 and box 2 and box 3, which can be written as this, which further can be written as 1 as this, 2 as this, and 3 as this. So now we have understood what is a quantum system, what is orthogonality, why the components of the vector will be 0, what is a quantum state, and what is a Hilbert space, and also how the electrons would be and how do we mention those states. However, there are two things which are still remaining, because a state can be a two-state or many-state system. We need to deal with something which is called a quantum bit or a qubit, and this state can not only be in these very favorable condition, it can also be in superposition, which I'm going to cover up in the next part of the video. I would immensely like to thank you for watching this video, and if you have liked this video, do not forget to subscribe to my channel and click on the bell icon to get all the notification from Physics for Students. You can also write to me for any kind of a clarification at this email ID, and this is where I'm taking live classes on exclusively on general theory of relativity. You can also follow me on my Facebook, LinkedIn, Instagram and Twitter account. Thank you very much for watching this video. Please do send me your reactions in the comment box, and don't forget to subscribe, and Physics for Students will be soon back with more such exciting videos. But till then, may the good Lord be with you.